Hey everyone, this is Mr. A, and today I want to talk with you about finding the domain and range of composite functions. Now, it's real important that you know how to find domains and ranges already, and also that you know how to compose functions, because I'm not going to be talking about either of those topics in this video. I'm just looking at finding the domain and range of a composite function. So if you need help with any of those things, find another video or some other resource online before you watch this one. So when we say composing a function, what we're talking about is putting a function inside of another one. So for this picture I have mapped out here, what we're looking at is g of f of x. And you'll often see that written as, right, so this is also the same as g of f of x, right, g following f of x. So f is getting the input first, and then g is going to get the input. I actually prefer this notation because it makes it real clear that the input goes to f, and then whatever f kicks out goes then to the function g. So what I've got here with these three ovals is I'm talking about in this first one the domain of f of x. All right, so f of x is a function. It's going to have its own domain, and anything in that domain we can plug into f of x, and it's going to send some inputs out to its range. So this oval represents the range of f of x. Now normally we'd be done there, right? We have a function, we talk about what can we put into the function, that's our domain, what we were going to get out of the function, that's our range. But since we're composing, the range of f of x becomes the domain of g of x, right? So everything that comes out of that inside function ends up in the domain of the outside function, or at least that's what we have to make sure can happen, because the outside function is going to start to try to work on anything that the inside function spits out. And then of course here, finally, we have the range of g of x. And so when we compose functions, the domain has to take into account both what goes into the inside function, f of x in this case, and also if there are any elements that the inside function might kick out that would cause a problem for the next function, the outside function, when we get to it. And then whatever comes out of the outside function, that'll be our final range. So let's jump into an example. I think you'll see what I'm talking about here. We're going to take a look at this pair of pretty straightforward rational expressions, this f of x, this g of x. And let's start by talking about f of, well, let's see, I've got in the picture here g of f of x once again. Right? So again, this is the domain for f of x. So you can think about these as things that we are putting into f of x. Now for this example, I'm going to have this oval represent all real numbers, and inside the red circles, I'm going to pull out any numbers that are a problem. So if you take a look at f of x right away in the denominator here, you can see that I'm going to have a problem when x equals 1. Right? If it's 1, then you have 1 minus 1. You're dividing by 0. That's not allowed. So I have to take 1 out of the domain. So again, this number 1 in the red circle, I'm pulling out of the domain. So I'm saying reals take out the number 1, because if I plug a 1 into f of x, I've already got a problem. Now that's what's going into f of x. But I also want to think about what's coming out of f of x, right? So what's going to come out of f of x? Well, in this rational function, we can think about end behavior. As x gets very large, to infinity or negative infinity, this denominator is going to get huge compared to the numerator. So this function is going to get closer and closer to 0. Right? If you were to graph this on your calculator, you'll see that it's going asymptotic. In fact, I can do a quick sketch. It's going to have at 1 a vertical asymptote right there. And let's see, to the right, x minus 1 is going to be positive. So this function is going to look something like this. It'll go to positive infinity there, negative infinity there, and on the ends this end behavior is getting closer and closer to 0. But because there'll always be something in the numerator, I'm never actually going to get 0. So while f of x I can't plug in a 1, I also am never going to get out a 0. Right? So 0 is not in the range of f of x. Take a minute and pause the video to make sure you're okay with that before you move on. F of x I can't put in a 1, and I can't get out a 0. So now we're going to switch focus a little bit and go to g of x, which is the outside function in this composition. So we're going to think about what can't I put in to g of x. Well, g of x, again, I have an x plus 3 in the denominator, so really quickly you should see that I can't allow x to be negative 3. Because if x was negative 3, then g of x is going to be undefined. Now that leads us to something interesting in the bottom. Notice this negative 3, I have an arrow pointing to it, and that arrow comes from the domain of f of x. Because what I have to do is consider, are there any values of x that when I plug them into f of x are going to spit out a negative 3? Because if there are, that's going to be a problem for me, since g of x can't handle negative 3. Hopefully that makes sense to you. So to find out if there are any values of x that are going to cause that problem, all I need to do is take f of x, which is 2 over x minus 1. And I'm simply going to set it equal, whoops, that's not how you write it, minus sign, 2 over x minus 1. And I'm simply going to set it equal to a negative 3, the value that I cannot allow it to be. Right? And if you like, you can make this not equal to emphasize that it can't be that. And then we'll just cross multiply and solve, right? So here we get 2 equals negative 3x plus 3. And so, let's see, minus 1, so 3x equals 1, and x equals 1/3. Of course, again, this is really not equal on all of these because we can't allow that to happen. So what this is telling me is if I plug 1/3 into f of x, then it's going to spit out a negative 3. That's a problem. So what do I have to do? I have to take 1/3 out of the domain of f of x, right? So I can't allow a 1/3 to go in there. So now there's two values that I have to pull out of my function's domain. I have to pull out the 1 because 1 causes a problem with f of x. I have to pull out the 1/3 because 1/3 produces a negative 3 once it comes out of f of x, and that's going to cause a problem for g of x. So now we've got the domain taken care of. We're going to continue on with this g of x, thinking about what's happening here. So g of x can't have a negative 3. All right. Well, notice f of x is never going to give me a 0. Well, that means that I'm never going to see g of 0 because g is only going to get values that come out of f of x. So if I'm never going to get a 0 for g to work on, then there's some value that g is never going to spit out, and I want to know what that value is. So I simply ask, what is the value of g of 0? Right? So g of 0 is 4 over 0 plus 3, which is just 4 over 3, or 4/3. All right, so again, what I'm doing here is looking at the 0 that's never going to get to g of x, right? I'm never going to get a 0 out of f of x, so I'm never going to have an opportunity for 0 to get evaluated by g of x, which means my range is not going to contain the value 4/3, right? Because g of x is never going to see that 0, it'll never get 4/3. What else isn't going to happen? Well, with g of x, just like f of x, it's a simple rational function, and the denominator is going to get really large compared to the numerator as x goes to infinity, positive or negative. So this function is going to approach but never get to 0, very much like f of x did. Only difference is the asymptote would be this time at negative 3, and other than that, the rest will look more or less the same. So I'm never going to get a 0 out of g of x, just like I never got a 0 out of f of x. And so now we can see this is our domain for the entire composition. This is our range for the entire composition. So what are my actual values? I'm just going to scooch this down a little bit. So the domain for the composition is all reals, take out 1 and 1/3. Right? Those are two different values, 1 and the value 1/3. So I've got to pull both of those out. For the range, it's going to be reals, all reals, take out the 0 that g of x will never give me, and the 4/3 that g of x will never have a chance to give me, right? Because f of x is never going to spit that 0 out. So there we've got our first example. I'll just put that all on the screen here together, right? So there we have our first example of a composition of these two rational functions. That's looking at g of f of x. Notice what we had to watch out for. Values that we can't plug into the inside function at all, and also values that we can't plug into the inside function because they'll cause a problem down the road with the outside function. Then we also had to consider values that we can't plug into the outside function, that we won't get from the inside function, right? And what's that going to do on our outside function, right? If we're never going to get a 0, then we're never going to get a 4/3 out of g in this case, and we're never going to get a 0 out of g for the same reason we won't get a 0 out of f, that had a horizontal asymptote at y equals 0. So let's take a look at the same two functions, but we'll reverse the composition. The work is going to be very much the same, but we'll get some slightly different answers. So now notice I have g of x for this first oval. That means that we're starting with g of x, finishing with g of f of x. So now we're talking about the composition f of g of x. Right, so g of x is now our inside function, and f of x has moved to the outside. So we're going to start by thinking about g of x. What can't we put into g of x? Well, we talked about that already. We can't put a negative 3 into that function. It'll be unhappy. What can't we get out of g of x? Well, we're never going to get a 0. That function has a horizontal asymptote at 0, so we're never going to get a 0 out. Now, we can do one of two things. We can go back here, or we can follow that 0 through. So for right now, let's follow that 0 through. If g of x is never going to give me a 0, then that means that f of x, the outside function, is never going to see a 0. We're never going to have a chance to figure out, or for the function to evaluate, f of 0. So what is f of 0? Well, f of 0 is 2 over 0 minus 1, which is to say 2 over negative 1, or negative 2. And that value is never going to show up in my range, right? I'm never going to get a 0 out of g of x, which means f of x is never going to get to work on that 0. So I'm never going to get f of 0, never going to see 2. Now let's go back to f of x and think about what we can't do with it. We see that f of x can't have a 1, right? Because then you have 1 minus 1 on the denominator, and that's going to be undefined. So to make sure that f of x doesn't ever receive a 1, right, then we have to make sure that g of x is never going to send f of x a 1. Because remember, g of x is the inside function. Whatever g of x does, its output, its domain, is going to become this potential range for f of x. So in order to make sure that f of x never sees a 1, we have to ask ourselves, is there any value of x that when we plug it into g of x is going to output a positive 1 for f of x? So to find out is pretty simple. All we need to do is take take g of x, 4 over x plus 3, and we're going to set that equal to 1. Right? That's this one right here. Put that over 1, cross multiply, we have x plus 3 equals 4, and take 3 away from both sides, you get x equals 1. So we can't allow x to be equal to 1, because if you put a 1 in to g of x, then you're going to get a 1 out, and if you get a 1 out, then f of x is going to have to deal with that 1, and that's going to cause a problem, right? So we can't allow f of x to see that 1, which means we can't allow a 1 to go into g of x, because if we do, then we'll get a 1 out, and f of x is going to have a problem. It'll be undefined when it goes to that outside function. So we can't plug a negative 3 into g, because g will have a problem. We can't plug a 1 into g, because that'll lead to a 1, which causes f of x a problem. We can't plug, excuse me, we're not going to get a 0 out of g of x, so that means f of x will never get a chance to work on 0. 0 would have led to negative 2, right, up here, f is 0, but that's never going to happen, so negative 2 is going to come out of our range. And then we also have to just think about what is the function f of x on its own never going to do, and again, f of x is not ever going to give you a 0 in the range for that same reason we talked about before. It has a horizontal asymptote. So now again, we can write down, let's see, bring this whole thing up. So when we talk about the domain and the range of these functions here, the domain of the composition is going to be all reals, take out, now we have to take out both of the numbers negative 3 and 1. So we're going to pull out negative 3, and we're going to pull out 1. The range for this composition is all reals, take out negative 2, and take out 0. So when you're looking at a domain and range for a composition, you have to be a little bit careful, because it's not just as simple as what goes in or out of one function. You have to make sure that nothing goes into the inside function that's going to cause a problem for the outside function. You also have to make sure that nothing goes in that causes a problem for the inside function. And the outside function, the same thing, right? You have to make sure that you don't put in any value that would just cause a problem for the outside function. So in this case, that would be like our negative 1, right? And you also have to think about what values you're not going to get out. That would be the 0 that's not in the range of f of x here. So that's an introduction to domain and range for a composite of rational functions. This is going to be part 1 for this series, and I'm going to do a part 2 where I look at some other variations where it's not just a simple rational and you have to be a little bit more clever. But if you keep this picture in mind of the input for the one function, right, and the output becoming the input for the next function, which ultimately gives you your final range, that'll come in handy as you look at any type of a composition. So I hope you found that helpful. If you enjoyed this video, please like, subscribe. If you have any questions, you can ask me in class if you're in my class, or just drop me an email or leave a comment below. Have a great day. a 1.